Welcome to the Space Telescope Public Lecture Series in our very first online-only edition. Today we have Benne Holwerda speaking from the University of Louisville, speaking on Rubin's galaxy, a gentle giant spiral galaxy. I'm your host, Dr. Frank Summers of the Space Telescope Science Institute, and the Space Telescope Public Lecture Series will be online only for the rest of 2020. And I want to thank the amazing team at Space Telescope for producing all of this. In special, our thanks to the amazing tech team, Thomas Marufu and Grant Justice, without whom this special online-only edition wouldn't be possible. So we have speakers lined up for the rest of 2020. Next month, in July, Amaya Morrow-Martin will be speaking on interstellar comets. These are comets that have come from other solar systems and entered into our planetary system. You're really going to want to hear that. That's going to be fantastic. In August, Quinn Hart will be talking about the physics of astrophysics. And I know that sounds really geeky, but she actually said, you know, that's sort of the topic that I'm going to talk about, but I'll give you a really cool title. So next month, we'll have a really cool title that won't sound so geeky. But actually, it's really interesting how much physics there is underlying the astrophysics and how the two things work back and forth. In September, Will Fisher will be speaking on the Ulysses project, which is a grand ultraviolet survey of stars. And it's one of the really big legacy projects from Hubble. And he'll be able to tell you all about that in September. If you would like to learn about these events, you go to our website, which is at www.stsci.edu/public-lectures, and you will get this web page. And we have just updated it for our online-only version. The webcasts, we've been doing webcasts, back to 2005. So that's 15 years of webcasts we've been doing. We've been doing YouTube webcasts since about 2013, 2014 timeframe. So there are links on the left side of this page to our YouTube playlist, as well as our webcast archives here at the Space Telescope Science Institute. And on the right, you can sign up for email. You can put in your email address and subscribe, and you'll get an email once or twice a month telling you when our lectures are going to be and when they have been posted on our YouTube channel. Lower down on that same page, you will find a list of the upcoming lectures and their details. The details of each lecture tell you not only the speaker and the abstract of the description of what's going on, but also after they are posted, we have links to the STSCI version of the webcast, as well as the YouTube webcast. Of course, for this year, for the rest of this year, the STSCI webcast will not be there. The email, as I said, if you can just sign up at our website to get announcements. An alternate way to get notified is to subscribe to our YouTube channel. It is youtube.com/Hubble Space Telescope, all one word. And that if you sign up, subscribe to that, you will get not only the reminders of these live events, but also notices of the new videos that we post there. Finally, if you have comments or questions, you can send them to publiclecture@stsci.edu. If you'd like to follow our institute on social media, we have channels for our institute as well as for the Hubble and James Webb Space Telescopes. They're on Facebook, Twitter, YouTube, and Instagram. I myself do a little bit of social media on Facebook and Twitter, and you can follow that if you'd like to know my thoughts on the world. Okay, now my favorite part, the news from the universe for June 2020. Our first story tonight, and what was going to be the topic of our public lecture in April, is Hubble's 30th anniversary. It was 30 years ago. I mean, wow, it's just hard to think about it being that long ago, but it was 30 years ago that the Hubble Space Telescope launched into orbit on the space shuttle. And each year we challenge ourselves to come up with a really cool image to celebrate. What are we going to do to top ourselves? Well, this year we came up with an amazing image. And this was the image that we came up with. It's a picture of the red nebula, which is NGC 2014, and the smaller blue nebula, which is NGC 2020. And this is really gorgeous. It's, hundreds of megapixels, all sorts of detailed. And when we were first looking at it, it sort of had this, brain coral type feel to it. And we sort of got, oh, well, maybe the NGC 2020 is this little jellyfish dancing around on a coral reef. And so the nickname came up to call it the cosmic reef. And I would tell you all about this image, but I'm not, because I've already done it. On the 30th anniversary, we did a YouTube webcast of the Hubble Space Telescope 30th anniversary image unveiling with me and Ellen Asabi describing Hubble and the 30 years and the details of this new image. So if you go to YouTube and type in Hubble 30 image unveiling, this will be your first hit. And you can watch a 30-minute presentation on the 30th anniversary image, which saves me from having to repeat all that during my News from the Universe today. Our second story, Betelgeuse is back to normal. If you were here in March, you saw that I talked about the red supergiant star Betelgeuse. Most of you may know that it is the right shoulder of Orion. It's on the top left in this image. It's a red supergiant star. And what I talked about then was the fact that Betelgeuse has been dimming, okay? On the left, you see a picture from February 2016, which is its normal brightness. And on the right, you see a picture from December 2019, which is a greatly reduced brightness. And so Betelgeuse had been dimming and people were going, oh my gosh, is it gonna explode? Is it gonna explode? And no, it's not gonna explode. It didn't explode. I showed at the time this graph here, which has brightness on the y-axis and time on the x-axis. And the green dots indicate the visible light observations of Betelgeuse. And it does vary up and down, but in 2019 to 2020, it dropped significantly. It dropped a full magnitude, okay? That's a factor of at least 2.5. So it was down, less than 40% of its normal brightness. And at the time I said, well, it looks like it's a giant dust cloud that's blocking it, and this should go away. Well, just to update you on that, here is the current plot, and it shows that Betelgeuse has indeed risen back up to its normal brightness, okay? So Betelgeuse is back to normal. It's not going supernova, but when it does, it's gonna be fantastic. So stay tuned. Eventually, we'll get to see Betelgeuse go supernova, just not in 2020. Our third story is also about a star. It's our star, the sun, and how it is actually arousing from its hibernation. Now, the sun usually has sunspots on it, right? And on the left side of this video, you can see the sun during the month of November 2011, and it has a large number of spots on it. This is sort of what we expect out of the sun, to have a lot of sunspots. On the right is the sun from February 2019. And I know it doesn't look like it's actually a movie, but it is. It's actually rotating just like the one on the left. But during February 2019, there were no sunspots at all for the entire month. The sun has been quiet, right? And this is normal because the sun goes through a solar cycle. It goes from minimum, where it has no sunspots, to maximum, where it has its greatest number of sunspots. This image is from the SOHO satellite, and it shows the sun in ultraviolet from 1996 every year through 2006. And you can see the amount of solar activity rises and falls over this 11-year cycle. Well, here's a plot to show you where we are in 2020. We're just finishing what's called solar cycle 24. And you can see the number of sunspots peaked somewhere around 2014 and has been falling ever since. Matter of fact, 2019 was a very, very quiet year in the sun. There were over 100 days recently where the sun did not have a single sunspot. And so this is what we call solar minimum. And we're waiting for the sun to come out of the solar minimum. This cycle, however, was also a relatively low cycle on the series of cycles. So we've been following sunspots for hundreds of years, and you can see that lately, the highest cycle is around, what, about 1960 or so. There was a cycle with a tremendous number of sunspots, but cycle 24 doesn't seem to be that great. And their red line, by the way, is the prediction that they expect for cycle 25. So we're waiting for it, watching it to see, is it going to come out? And on May 29th of this year, the Solar Dynamics Observatory got these images showing activity on the upper left here of the sun. And you can see that there's a wonderful amount of magnetic activity showing that, hey, the sun might be starting to come out of it. Does this mean that it's going to come out of it? No, it could just be an isolated region that comes and goes away. Or it could be the start of cycle 25, which should begin relatively soon. It just goes to show you that the sun is not static. The sun goes through changes, and it's a wonderful process of science being able to sit and watch and study and explore those changes in our own star. And now bring you to our featured speaker. Benne Holwerda is currently at the Department of Physics and Astronomy at the University of Louisville. He got his PhD at the University of Groningen in the Netherlands. And then he came to our institution at the Space Telescope Science Institute and did a postdoc here for several years. He has kind of been a world traveler in what he's done. After the Netherlands and the United States, he went to Cape Town. He went to work for the European Space Agency. He worked at the Leiden University. And then finally, he came back to the United States to his job at the University of Louisville about 3 years ago. Benne and I worked together a little bit while he was here. He's a wonderful guy. And I asked him for something interesting and fun to tell about him. And he said that he learned to fly a plane. He has his pilot's license from another astronomer. So he may exceed in flights of fancy, not just in science, but also actual flights. So ladies and gentlemen, Dr. Benne Holwerda.
Thank you. All right. Thank you very much. I'm trying to shift gears really quickly here. Thank you for having me. I know Frank for a long time, so as soon as he said any volunteers, me. So I'm very glad to be talking to you here about Vera Rubin's galaxy. The phone number for that is UGC 2885, but we've been calling it Rubin's galaxy since January. And I don't do this alone, far from it. I do this with Rupali Chandar, Pauline Barnby, Savik Ford, Jeremy Balin, and Molly Peebles. Those are my collaborators at the beginning for this project. And then we have a bunch of students working on this: Kyle Hixenbauch, Sean Knabel, Alice Jacks, and Ren Mullins. So it's a team effort that we've been working with, and I've been working with the Space Telescope Science Institute. So the talk is kind of a two-parter. One, I'll explain to you who this Vera Rubin person is first, and then why we hopefully become clear why we wanted to name a galaxy. We didn't officially name it because there are no official names, but there are lots of nicknames for galaxies. So this is kind of now the unofficial nickname for this particular galaxy. And if you actually want to talk to me later, have a question, feel free to either use Twitter or email to send me a question later. So who is Vera Rubin? Vera Rubin was one of the first, was an astronomer in California, and she published one of two major findings that showed that dark matter in galaxies actually exists. She looked at the rotation, how fast galaxies rotate around using spectroscopy, and she was one of the two people that advocated that these galaxies had things other than the stars that we can see. And in the picture here, you can see. And I always look at these things and go, like, they must be staged because the lighting's so good and they're clearly not working in a shadowy observatory. But you can watch her here, examine photographs here, but what she was mostly known for is spectroscopy. And the second thing, and this is something that is reoccurring, I have encountered her one time, and she was incredibly encouraging. This was back in 2005. I was finishing my PhD, and so you're nervous, and I was talking about my topic, and she goes, "Oh, wait, hang on." And she dives into her bookcase, comes back out and says, "Look, Hubble was struggling with the same thing." And I don't know, just that little push kind of really gets you through the last bits of a PhD. And so she was, and my story is far from unique. In fact, everybody I've talked to said that she was invariably encouraging and supportive of young astronomers of any stripe to go do science. And so she was a very impressive scientist. For these two characteristics. So she was known for the spectroscopy, and I love this kind of like more candid shot where they're debugging their spectrograph at the back end of this the large Lowell telescope. And what she did mostly was take spectra like these. And spectra are the fact that you take a point of light and you spread it around in wavelength. So then you can see the fingerprints of various chemical elements. So for example, at the bottom you see H, which is hydrogen, and then alpha and beta mean that they are different kinds of lines, but the fingerprint of hydrogen is pretty clearly visible, as is oxygen in some of these spectra that she's taken. And I want to take you to the orange line. The orange line is where we expect hydrogen to emit light. And then you'll notice that some of the smudges are a little bit to the right. They're redshifted. They're in longer wavelengths. And some of them are a little bit to the blue side. They're blue shifted. So this is what happens when the Doppler effect takes effect. If something's moving, if it's moving towards you, the wavelength gets shorter, the pitch gets higher, they're blue shifted. And if they're moving away from you, the pitch gets lower, they're red shifted. So we've been looking, you can see movement using spectroscopy. And very carefully, they did this for our nearest neighboring galaxy, Andromeda. You can see the photographic plates on the left here with all the points that they took a velocity measure of. And then on the right, you can see the distance to the center of Andromeda and how fast it's moving away from us. It's all moving away from us, but it's moving at relative speeds. So some of them are moving towards us and some of them are moving away from us. In fact, as you plot everything along this line, you'll notice that on one side of the galaxy are redshifted, they're moving away, and on the other side, they're all moving towards us. So Andromeda is rotating. And not only is Andromeda rotating, you sort of expected that, but it's rotating, and the speed at which all the bits are going is roughly the same, no matter how far out from the center you go. You'll notice that it's fairly flat. They're all kind of going at the 300 kilometers a second speed in the redshift, and they're all going about between 2 and 300 in the blue shift, but it doesn't quite matter how far away from the center you are. Now, if you find this in one galaxy, if you find something strange in one galaxy, you can kind of write it off and say, I guess that galaxy is just strange, and move on with your life. Because you know that all the galaxies don't behave like that. However, at the same time, and the groups were definitely talking to each other, the Westerbork radio telescope was taken into operation. Ron Allen, my PhD supervisor, was intimately involved in that. And they were also looking for hydrogen, the imprint of hydrogen, but in the radio. And in the radio, you can also measure Doppler shifts. So they did the exact same experiment on different galaxies. So here's an example, NGC 4736, another phone number. We haven't named this one, but as you go further and further out from the center of the galaxy, you'll notice that the gas moves with about the same speed. In this case, it's almost 200 kilometers a second, and it roughly stays pretty flat, no matter how far out you go. And that is kind of surprising, because if you assume that all the mass is associated with all the stuff that gives off light, which it is true in our own solar system, for example, you'd expect the dashed line here. If we just say all the mass that's in there, that's all the stuff that's in this galaxy. And if I'm looking at something that's orbiting around it, it can't go any faster than, say, I'm 30,000 light years out. It can't go any faster than 50 kilometers a second, because otherwise it would fly off. Otherwise, there's just not enough stuff within it to keep it pulling into its orbit. And yet, we look at the observations, we look at the blue points, for example, from radio, and we look at the yellow points from starlight. They're going much faster than they should be able to. And the fact that it's flat means that there is more and more things, despite the fact that the amount of stars seem to drop off pretty quickly, there has to be more stuff there just to keep the gas from flying off as it's rotating around the disk. And so that's a bit of a mystery. You have to have something that isn't stars, isn't gas, isn't giving off light, and we don't know what it is. Hence dark matter. And this was the best evidence for dark matter. And as just to compare, if like we're looking at our own solar system, 90% of all the mass is in the sun. So everything rotates around the main mass, which is essentially all in the sun. And so if you're close by, you whip around it. And as you go further and further out, you go slower and longer orbits. So Pluto is only going at 10 kilometers a second or less, and then Mercury is whipping around there with 45 kilometers a second. So, and even if you look at the top here, so you can go look from above, you see, like the solar system, you see the movement going on the left-hand side, and like the way the galaxies move, it's on the right-hand side. And you can see that galaxies don't move like the solar system does. We are definitely in trouble. Our galaxy, despite looking like a giant ball of stars with just some stuff swirling around it, is not moving like the solar system is. So the mass is distributed differently. So galaxies don't rotate like a solid disk. I love the example of a clay spinner, because we used to say record player, but I don't think anybody knows what a record player is anymore, except for some audio files. And so maybe you've done this, and you'll notice that if you put the clay further out, it'll definitely spin off the wheel. So a pottery wheel, you have to put it right in the center, but as you go further out, it's moving quicker. And if they don't rotate like the planets around our sun either, so something in between. It's something between a solid disk and putting everything in the center, which is strange, right? So this was definitely a bold claim to say, like, well, most of the mass doesn't glow up, isn't sitting in stars. And this is the seminal study from Rubin in 1980, the 1977 or 78, Albert Bosma produced something very similar. So basically both these groups had plots like this, where you go from the center of the galaxy, and each line here is a galaxy. So instead of saying, well, I guess Andromeda is just strange, let's go check it in other galaxies and see if they do the same thing. And they do. They all sort of flatten out the further out you go. They go up really steeply, the velocity whips up, and then it just flattens out and stays there. And the further out you go, it still stays at pretty much the rotational velocity here that you see. So they're all flat. And one of them kind of sticks out because it's right at the top, and that's UGC 2885. Other than that, the fact that it has the fastest rotation in her study, it doesn't really stand out. It's a normal spiral galaxy. It's got that lovely flat rotation curve, and that's it. Of course, we check each other's work. We're good, conscientious scientists. So as soon as one group claimed, hey, this galaxy is rotating flatly, we're going to go check that with the radio telescopes, and the radio telescope results were checked with spectroscopy. So the rotation curves were confirmed for this particular galaxy right after, well, pretty quickly after 1980. And so they're all agreeing that, yes, this galaxy rotates between 250 and 300 kilometers a second. Doesn't matter how far out you go. You can keep going, keep going, keep going. It just rotates at that speed. So very interesting, cool result. Galaxies don't rotate like solid disks. They don't rotate like our solar system. And that comes to the Spider-Man rule of science. Extraordinary claims, basically saying all the mass isn't sitting in stars, it's sitting somewhere else. They require extraordinary evidence, not a single galaxy, multiple galaxies, not a single kind of telescopes, multiple different telescopes, not a single group. Both groups find the same thing. And so it's an amazing discovery by the various scientists of the time. Like this took very careful work. And so that finally cleared the threshold of saying like, yes, there has to be some additional ingredient whenever we bake a galaxy. So the Spider-Man rule was adhered to, but what does this all have to do with the Hubble Space Telescope? Nothing so far. All of this was done in the 1970s when the Hubble Space Telescope was a dream of the early pioneers like Nancy Roman, and they were looking at how to build one of these things. And one of my favorite things of the Hubble Space Telescope history is they used to have a drawing with a little astronaut in the back of this thing, changing out photographic plates like he is, you know, Vera Rubin, but now in space. I'm so glad they don't do that because we don't visit the Space Telescope anymore, and that would be a very unhappy astronaut. But there's a Hubble Space Telescope. This is where it comes in because Vera Rubin wrote 2 papers in 1980, and I read the second one. And so the one is on the rotation curves in dark matter. It's the one that we all look at, and it's the seminal result. And the other one kind of just notes that this particular galaxy is really big compared to all the others that we know of. And so this is a picture from that other 1980 paper where you see M81, that's a very well-known spiral galaxy, our own Milky Way, it's about 25 kiloparsecs in diameter. M51 is a bit bigger, 35 kiloparsecs in diameter. M104 is the Sombrero galaxy, it's 40 kiloparsecs in diameter. M31, the Andromeda galaxy, 50 kiloparsecs in diameter. And M101 is another crowd pleaser, this lovely face-on spiral galaxy, and it's 65 kiloparsecs roughly in diameter. What she noted was that it's 250 kiloparsecs in diameter for UGC 2885. So that galaxy is really, really big, except that it looks like it's rotating like any other galaxy. It's just all the way at the top. It just seems to be well-behaved spiral galaxy, just really, really large. And so what I noticed when I was looking at this idly, I'm like, well, we've got a nice Hubble picture for M81, M51, M104. We've got like a third of M31, and we got all of M101. So we have beautiful Hubble pictures for all of these galaxies, except for UGC 2885. So why wouldn't it be a good idea to go look at the biggest spiral in the local universe? Let's go have a look at that and see if we can figure out how you make something that big, how you make a disk that big. So that's the result that we did. This is the this is the Hubble picture of Rubin's galaxy, and the other idea was to use it as a little tribute picture for Vera Rubin, who passed away in 2016. So you can see a lot more detail, of course, in the Hubble picture. We opted for a color option. And so you can see all the various, the components for a spiral galaxy. You see the bulge in the center, you see the disk, you see the spiral arms. I'll just take you through this Hubble picture now first. Where can you find this? And this is a question I always get from the amateur astronomers here in Louisville. We have a very active group. You can see this with binoculars or a decent amateur telescope or enthusiastic telescope. It's in Perseus. And so you see all the Milky Way stars here. There's a warrior. And as you go towards his foot, you can start seeing some smudges, and then they did this lovely fade here as we go to a modern picture, and here we are with the Hubble picture. So it's a pretty small smudge on the sky, but you can actually see it, and you can actually see that it has blue edges. It's a little trickier to see because of that bright star in the foreground there, but you can definitely find it with a telescope and binoculars. So how do we grow a giant like this big? Rubin's galaxy is so much more massive. It's 10 to the 12, so a trillion solar mass in stars, and it's much more extended than any typical spiral galaxy, certainly in the ones that we typically look at with Hubble or other telescopes. The question now is like, how do you grow this disk so large? Typically, if we want to get a trillion solar mass galaxy, we just smash two smaller galaxies and maybe throw a third one in, and then we end up with 10 to 12 solar masses. And usually they're in a giant blob. They're an elliptical. And mergers leave a mark. And this is such a regular, undisturbed looking galaxy that it's strange to not see any merger remnants, but maybe we can see that in the population of globular clusters in around this galaxy. And so that's the one that's the science we wanted to do with this picture. And so I stuck the result in, because I'm going to tell you about the result, and I'm going to tell you how we got there, and then I'm going to tell you the result again. We see very few globular clusters for a galaxy this size. So it actually implies that it didn't do any merging, didn't do much mergers. I love the fact that as soon as Hubble releases a picture, people have a go at doing creative things with it. And so with this picture, I love this 3D-ish view. I have no idea how people did this, but it does kind of show you that we're looking at a three-dimensional structure. We are not just looking at the stars, which the bright stars are all in the Milky Way. Anything with those diffraction spikes, those spiky things are coming out. They are definitely in our own Milky Way. And then we get this big galaxy, and then in the background you see all these smaller galaxies. And so you kind of see the whole universe in a little slice there. And so here we're back at the actual picture, and I'll take you through the various components. So I'll start with the center. And so the center is quite interesting because we see a lot of dust here. And brown stuff, those dark, veiny looking things that are swirling throughout this disk, they're molecular gas and dust. And I started my career studying dust in galaxies, so I'm super excited to see a beautiful example like this. You see the kind of tiger stripy pattern in between. There's clearly a lot going on here, but not only that, we can see the blue peaking in between. And the blue means young, recently formed massive stars. So we see that this galaxy is forming stars almost all the way to the center of it. And it has gas reserves to do that. And so you see young blue stars and new gas sitting ready to go. And so you've got both of those mixed together throughout the disk. So there's star formation isn't going on at any particular point. It is just spread out through this entire giant disk of this galaxy. No particular point has a lot of star formation, but almost all parts of the disk seem to have some. And there's our, it does make the picture quite photogenic, but as an astronomer, I kind of wish that I could wipe this thing off for a little bit, because we kind of would like to see what's underneath, but unfortunately we can't do that. There's no information below this really bright star. And I think that's the reason why we didn't look at it before with Hubble, because we're a little nervous pointing Hubble at bright things just in case we damage the camera. But I want to point out that the spiral arms are made out of still more blue stars, still the occasional O and B type star, brightly shining as it's just been formed. And there's these little clusters of them all throughout these spiral arms. They're beautiful, but it also means that this galaxy has never really stopped forming new stars, but it does it at a very gentle pace. And whipping around to the other side of the image, these are the background galaxies. So we see the foreground Milky Way stars with the spikes, and in the background objects like this elliptical galaxy kind of lurking in the corner. That galaxy is very far away. It has nothing to do with Rubin's galaxy at all. And there's even more distant galaxies that you can kind of spot here throughout the image. And I started my career looking at dust, started my career looking at the background images. This is what I was looking for, these tiny little smudges. So every time I get a Hubble image, I again go, oh, there's one, there's one. I'm not going to do anything but there's one. But what we're looking for here, you see a few of these little red dots. Those are the, some of them are still foreground stars, so we have to select those out. Some of them are parts of background galaxies, but really there's a few round, you see a few round dots here, and those are the globular clusters floating around this giant spiral. So there's lots of detail, there's lots of information in, apart from just being a gorgeous picture. We can see the 4 spiral arms. We can see that there's star formation happening throughout the disk. We see that it has lots of fuel to keep doing this. And we can see that it has clusters floating around it. And so the clusters is the things that we're after. I'll give you a quick look because the picture does not come off Hubble looking like that. It comes off as black and white pictures. And here's our observation design. Hubble has 2 main cameras, the wide field camera 3 and the advanced camera for surveys. The advanced camera for surveys went on in 2005, so it is now 15 years old. And with the 3 is a little younger. It went on in the last servicing mission. So you can take pictures at the same time. So we took the main picture, that's the green triangle, sorry, that's the green square here. That's where the galaxy is, but we also are looking for globular clusters very much further away from the galaxy itself using the advanced camera for survey. So we have more information on this galaxy. It doesn't come out very pretty the first time I tried to do this. The cameras don't quite align. I got diffraction spikes from the bright stars. I got secondary reflections from the mirror. There's a chip gap. So with the help from the wonderful people at Space Telescope, we cleaned it up some, and they just get the stretch just right so that you can see both the bright stuff and the faint stuff at the same time. I do kind of love how you can stretch that right. And so this is the black and white picture you get, and you get that in 3 filters. So you get it in blue, you get it in green, and you get it in red, and then you combine the 3 of them into a red, green, blue RGB image, and so that's how you can get a color image. So we have blue isn't quite blue, green isn't quite green, and red is a little bit near infrared, but they are as close as our eye perceives these colors. So they're real to as real as I can make them. And so we had the big image release at the American Astronomical Society meeting in January. This is back when they still let us out of the house. And it was quite exciting to share this with the world and share just something pretty. But we also talked some science and all the things that we can do with it. And it's really fun when you actually meet people in person and then start collaborating with them. However, this project got started on Twitter. I just chatted to a couple people on Twitter about this, and before we know it, we had a Hubble proposal written. So you can do things in person, you can do things online, and I guess we're showing that. But here's back in person. This is some of the people that I started this project with. From left is my student Sean, Molly Peebles, Pauline Barmby, Jeremy Balin, and myself. Because the Space Telescope had this up at a life-sized picture. So that was just too cool not to take a picture of. And then, of course, if you have something like this, it goes into the various media, and you obsessively check and refresh things until you realize that it's all over, and you can get to see your own picture back and not be able to read anything except Hubble in the press releases. So that was kind of cool. And when I was an undergrad, in 1995, the NASA started the astronomy picture of the day. And it hasn't really changed format. It looks exactly the same. It just publishes a very neat astronomy picture every day. Starting as a student of astronomy, I was like, well, maybe one day when I grow up, I'll have my own astronomy picture of the day. And lo, I do finally have one 25 years later. So cross that off past self. So that was really, really fun. So I talked about the fact that this galaxy is so big for a spiral galaxy. And this is the Hubble tuning fork. This is the way that Edwin Hubble back in the 1920s classified the galaxies that he saw on his photographs. And so on the left-hand side are the ellipticals. They are basically giant American footballs or rugby balls, depending where you are on the continent. They are flattened elliptical things, and it really depends on how you look at them. Those are the left red and dead galaxies. They're orangey. They're made out of old stars, and as you go further to the right, you get more things that are basically flatter, and they are disk galaxies. And Rubin's galaxy is essentially an SC galaxy. So at the top right, it doesn't have a giant central bulge. It just is mostly made out of disk and arms. But if we are looking for the biggest galaxies, we typically find them on the left hand side. They're ellipticals. The biggest galaxies are ellipticals. So how do you get an SC to compete in the same weight class as ellipticals? So that was kind of the question. So I looked at, this is a plot of all the nearby galaxies from the 2-micron all-sky survey. And there's star-forming ones, and there's quiescent. Quiescent means not doing very much star-forming wise. And there's kind of two groupings here. You can kind of see that there's a line of star-forming galaxies, and there's a line of quiescent galaxies. And those star-forming galaxies are mostly spiral galaxies, and the quiescent ones are mostly elliptical galaxies. And so as you go along the spiral galaxies, you suddenly kind of peter out, and then there's a few really big 10 to the 11 solar mass galaxies. Like we call those super spirals. So that's as big as we can grow them, except that you then can do another step of 10 and get 10 to the 12, a trillion solar masses of stars, and then you get a Rubin's galaxy. So it's even big for a super spiral. It's a super spiral. And then but it's not making stars exactly like you expect a spiral galaxy to do. It's just sort of underperforming a little bit there. But still, it's got 10 times more stars than the typical super spiral. So how did it get there? How did it make so many stars? The super spirals look like this. And most of them, I think the technical term is train wreck. It's really when a galaxy has smashed into the other one. You can see on the left-hand side, for example, two bulges. Essentially, that's two galaxies as they are smashing together. In the middle, you can see, well, if that's a disk galaxy, I'll have to squint a little bit because, it's all twisted and strange looking. And even on the right-hand side, despite that looking a lot more like a normal spiral galaxy, it doesn't have really the spiral arms that in a regular pattern that definitely has been perturbed by some nearby companions or after eating a big meal, basically merging with another galaxy. And that seems to be a pattern. Super spirals tend to be survivors of a recent merger, and the only reason that they're pumping out so much new stars is because they've just swallowed a companion galaxy. So the super spirals, it doesn't seem to belong to. It's not forming the amount of stars as the super spirals do. It is much bigger than the super spirals. Everything else, even remotely in its weight class, is an elliptical. So how do you do this? How do you make a giant disk galaxy? How did you get there? And so I go back to what we know about how galaxies form. We know that galaxies form in giant dark matter halos. So as soon as we learned from Rubin's results and Albert Bosman's results that galaxies have dark matter in them, we started making universes in the computer that have dark matter in them. So you start with a giant amount of dark matter. You see that on the right-hand side, that's where the dark matter lives. And then you start following where the stars are. And you see that the galaxies sit in the same position as where all the dark matter is coming together. But you notice something else as well. If you have a big thing of dark matter, smaller bits of dark matter fall into it, and they are taking their stars with them. So stars, if you have a big galaxy, it should be eating and should be acquiring all these smaller galaxies and then encountering other galaxies and then smashing into them. Like, it's a very violent process, the life of a galaxy, it seems to be. So how do you make a galaxy of a disk which doesn't seem to have been troubled by anybody, doesn't seem to have eaten any smaller galaxies recently either, when this is how you know galaxies form? You know that they start as separate blobs of dark matter, and they come together as small in bigger and bigger chunks. So this is maybe this is an exception. Remember, we only have the one. So maybe it's just eaten lots of really, really small galaxies. And this is what you then expect. You expect all these smaller galaxies are Rubin's galaxies, the green circle in the center. And then you throw all these smaller galaxies at them. And they get completely shredded to pieces. As you can see, they're all in these streams, and in these, all the stars get flung all over the place. And this is all by tidal forces. So you expect this, basically, if you looked deep enough. But even with the Hubble Space Telescope, at the distance where Rubin's galaxy is at, we wouldn't be able to see the streams. We wouldn't be able to see the fuzzy plumes, because they're just so spread out. However, so here's what these fuzzy plumes, this is sort of what you expect. You expect something like this. So you expect shells, you expect plumes, you expect streams of stars, but they're all so dim that we can't see them. But how can we see if they have this? Well, every galaxy has clusters around it. Every galaxy has globular clusters. And so what we can do is look for the surviving globular clusters of these galaxies that the big galaxy has eaten. And so this is the Sombrero Galaxy again, and people have studied this in detail and looked for all the globular clusters around this big, again, similar mass, not quite similar mass, but big elliptical S0 galaxy. And you can find a lot of globular clusters. It has eaten a lot of its companions, clearly. So this is what a globular cluster looks like in our own Milky Way. It is a heap of stars in a spherical grouping. So they're always nice and round. They all formed at the same time, and they all stick together. And so you look for these small blobs of stars, and they look like not quite a star at the distance of Rubin's galaxy. The nice thing is we have color information, so we know that they're supposed to be a certain color. We have blue, green, and red, so we can see if they're in the right part of color space. For example, we compare green versus red and blue versus green. That's the x-axis is V minus I, that's the filter names, but that means green minus red, and B minus V is blue minus green. And so we say, all right, the points that I'm seeing, where exactly do they live? We know that the GCs, the globular clusters, are living in the ellipsoid in the center. And there's two kinds. There's bluish ones, they're a little younger, and there's reddish ones, they're even older. And so we go tally how many of those we see. That's the trick. We're going to go see how many globular clusters Rubin's galaxy had, and do we see its leftovers? Essentially, we're looking in Rubin's galaxy's fridge and seeing if it's got any leftovers from all the big meals that it's had. And also what we're going to do is see how bright they are, and see how many globular clusters they are, and if that, which galaxy, other galaxy that we know it resembles most. So this is green minus red, the color, and then we also see how bright these clusters are. Because if there's lots of really bright clusters, well, that tells us that there are more recent arrivals, or if there are lots of faint ones, then they're much longer and much older ago. So we got blue and red globular clusters there. Okay, so this is from my colleague Jeremy Balin. He modeled how many we see. So there's a few. They start at 20th magnitude. If you are an observer, that is hard to do with anything other than a really big telescope or anything in space. And that's where our globular cluster count starts, and it ends at 26 magnitude. So we're actually going pretty deep. We're going to we find a pretty good tally of them. And We then compare that. So this is the histogram of absolute magnitude. So how bright they are if you would put them at a certain distance. So we can compare them with the other numbers of globular clusters in other galaxies. So we've looked over the years, and Hubble has done this since 2000, I think. It has taken tallies of nearby galaxies and tallied up their globular cluster counts. How many do they have? How bright are they? My colleague Rupali Chandar is the world expert on this, and I also know her from Space Telescope days. And so she and I will be comparing these counts. So as you look at that, you look at where M81, one of the beautiful disk galaxies in their local neighborhood, they're all much fainter than the ones in the Rubin's galaxy. The ones in M51 are pretty close. The one in M83 are pretty close. But those two, M101 and M81, are the bigger galaxies, and the M51 and M83 are all the smaller disk galaxies. They're much lower mass, and yet they resemble the closest to Rubin's galaxy. So the strangest thing is that as I do this comparison, and I'm looking at like the size chart here, there's no progression where you go from the smallest M81 numbers to M101 and then compare to Rubin's galaxy, because it doesn't look like the bigger galaxies. It doesn't have the globular clusters like the big spirals do. And it doesn't really have that as the smallest one either. It's somewhere in between. It looks like M51 just hulked out, just really, really big, just not violent. It has just slowly grown over time. That's the conclusion that we're getting. It is really like a normal disk galaxy, but smaller. And kind of impressive that it managed to grow that size without encountering anybody. This is the most complicated plot I'll show you, I promise. This shows on the x-axis the brightness of the galaxy, and to the left are the brightest galaxies and to the right are the dimmest galaxies. And it's because it's in magnitude, the more negative the number, the brighter it is. But if you don't like that, you can look at the top, and there in scientific notation is how bright it is in solar luminosities. And so in solar luminosities, UGC 2885, Rubin's galaxy, is about 10 to the 10. But in mass, it's a bit bigger. And so if you look on the y-axis, we get this strange t value, and t is basically how many clusters do you have per million solar masses. If I add another million solar masses to this galaxy, you get, there's X number, there's 10 to the 10 or 100 globular clusters that go with it. And so what people have noticed in looking at all these different studies using often the Hubble Space Telescope, that in the blue points and the black squares, the squares and the circles essentially are the dwarf galaxies. And dwarf galaxies for any, per million solar masses of stars, they have about between 10 and 100 globular clusters. So they have a lot of globular clusters for their size and then if you start smashing them together, as you're trying to make a bigger galaxy by smashing lots of dwarf galaxies together, you should get more globular clusters. Even if you destroy a few, they're pretty resilient. They should stick around. And so that's what you end up with on the left-hand side. Here, all the triangles are elliptical. So on this side is where the ellipticals live, and they are made from smashing lots of dwarf galaxies together. So per million solar masses, they have the same number of globular clusters, give or take one or two as they, sloppily get eaten, but that's okay. But here's UGC 2885. It's sitting all the way at the bottom of this plot. It has the fewest numbers of globular clusters of any galaxy we know. It just doesn't seem to have as many per million solar masses. So it hasn't been made by smashing the blue and red points together in order to make the ellipticals. It hasn't been made that way. It's actually sitting well below that. Now that is a little interesting because our whole paradigm is that in order to make big things, you smash smaller things together. And so what we think is happening is that we're looking at this galaxies like this one, and we think streams of gas are arriving out of the intergalactic medium. These are called cold streams, and there are now a major hunt going on in the radio astronomy to see if we can find these streams. But instead of having those little galaxies in them, in the case of the Rubin's galaxy, it was just gas. There's just gas flowing into this disk, and it's been doing that for billions of years as it just slowly grew in disk size and slowly grew by slowly converting that gas into stars. So a gentle giant. It has not been fiery eating giant meals. It has been snacking since the dawn of time, turning all this into its giant and beautiful disk. So we think that this is the best solution for how you can make a giant disk galaxy. You don't have to Hulk smash here. It's in fact quite non-violent. And then I did some sanity checks. I looked at the stellar mass, so you can see it's just over 10 to the 12, and the x-axis is solar mass. On the y-axis is basically size. So the bigger, the better. The bigger the more massive, the more extended. That seems to hold pretty well. These are all the relations that different people have found, and my little three-corner shape is Rubin's galaxy again, and it's right on where the averages are, except that the average for those mass galaxies has been determined from elliptical galaxies, but it is the right size for its mass. So nothing strange going on there. It hasn't been stretched out or anything like that. It is the size that you expect it to be. Is it maybe rare? Well, it is definitely rare in our local universe, because as you can see here, the x-axis is more distant. So as we go further and further out, again, the grayscale is the two-mass local galaxy survey, and the brighter galaxies are at the top. It kind of peters out as you get to the brighter galaxies, and it is definitely one of a kind in surveys like this. So it seems to be sitting in its own corner of the universe, doing its own thing, being quite unique, which is quite nice to see. How about its environment? Is it particularly lonely? So we look at the y-axis is a measure of how lonely galaxies are. We say the fourth nearest neighbor. I had to explain this to a student the other day. If you want to know how crowded your environment is, you go figure out not where the nearest other person is. The nearest other person in my case is downstairs. The next person over is also downstairs. The next person after that is also downstairs. They're all on their screens. But the fourth nearest neighbor is my next door neighbor. And so the fourth person near you, if you're sitting in a crowded auditorium, you can probably touch the fourth nearest person to you. And so you know it's crowded. If you can, in a subway, for example, if you can touch the fourth person nearest to you. But if you're living in the suburbs, the fourth nearest person to you is definitely one house over. And if you're living in the countryside, it might take a short drive for you to get to the fourth person nearest to you. So the fourth nearest neighbor is a good way to see if you're living in a crowded environment or not. And the distance to your fourth neighbor is, for this galaxy, I don't know, it seems to be not in a space where most galaxies seem to live. They're all smaller, but they're also kind of in a whole range of crowded fields. It seems to be that it is not particularly unique. I thought that I could find a way saying like, well, it doesn't have any friends, it's sitting off in the corner, but it seems to be fairly common density. So how do you grow this giant? It is so much more massive and so much bigger than any typical spiral galaxy. And I am talking 10 times more massive 100 times more massive than any spiral you care to name. And it's also 10 times bigger than anything else in the spiral galaxy range. So the question is how you grow that, and without mergers, mergers should leave a mark either in the population of globular clusters or in the disk itself. We don't see either. And so the fact that we see so few globular clusters is implying that it has actually grown very gradually over time. We don't see the remnants of any big meals. So that is interesting. So apparently you don't need to smash things together in order to make a big galaxy, and there's another way. And of course I have a next question, because as always with science, there's a next question. And as I look at this galaxy and I go, wow, this is a really big galaxy. What's the other thing about big galaxies? The other thing about big galaxies is they have a really big supermassive black hole in the center. Does this guy do as well? All the big, the picture of the black hole picture that you saw a year ago, that was an elliptical galaxy. And we know that, for instance, our own Milky Way has a supermassive black hole, but I'm really curious if this guy has a supermassive black hole. Has it grown with the galaxy itself? Is it a supermassive black hole that's typical for a 10 to the 12 solar mass stellar thing? Or is it just like M51? Is it just like M83? Like, is it really just a smaller disk galaxy black hole? How does that work? And that's the thing that I'll be working with Savick Ford at AMNH, the Museum of Natural History on. So that'll be really interesting. So we always have new things to explore with this, and we'll use other telescopes as well as the Hubble picture to go study now the center of this galaxy. All right. Thank you so much for listening to me. This is the inevitable selfie in front of the galaxy. If you get a poster that's bigger than you have to take a picture of that. That is just, that's the rules. So I really thank you all very much for listening, and I'll take questions if you have them.
All right, that was wonderful, Benne. We really enjoyed what a really deep tour of a very unusual galaxy. Although I have to tell you that when we first came up in the news meeting that we were going to present this, we looked at that big bright star with the spikes all over in front of it. Yeah, and we referred to it as a star-crossed galaxy. I knew you'd appreciate that.
I do understand that this is not the first galaxy you would point your bright, shiny new telescope at because of that star. You'd be worried that you just damaged the camera. But we did a careful check throughout to make sure that that didn't happen. But it is very hard to look at the galaxy with such a bright, we're kind of squinting at our screen half the time. Mm-hmm. It is, but it's pretty.
Yeah, it's wonderful. So I got a question from, as somebody who worked on galaxy formation and development over time. It sounds like what you're saying is this is a quiescent galaxy, right? This has sort of formed quiescently, which sort of means that, you know, it forms generally out in a voidish area because you're not going to have the things smashing in from all directions. But you then show the fourth nearest neighbor statistic, and it's not that atypical for a fourth nearest neighbor statistic. So it doesn't sound like it's in this void region. So, I mean, what's going on here, dude?
Okay, so if you only have one galaxy, then you have to take into account that you might just be looking at a very lucky galaxy. And I think this is what happened. I think it just narrowly escaped smashing into anything else.
Okay.
It's not, I have Julian Del Canton has a saying that's like, every galaxy's strange as soon as you get to know them. This is true for people, astronomers, and galaxies. This galaxy might just be lucky. It hasn't, it's not quiescent as in it doesn't form stars. All the blue stuff that you see is new stars. It's making new stars all right. It's just hasn't smashed into anything, but it even hasn't smashed into anything small as far as I can tell. It hasn't gone and eaten something like the Magellanic Clouds, for example, which is what our Milky Way has done. And Milky Way has two major events in its history already, and it's a lot smaller than this galaxy. It has the Sagittarius Stream, which is a large Magellanic Cloud size collision, and it has the Magellanic Clouds falling in right now. So it's got two of these events happening, and as far as I can tell, this galaxy has just dodged all of it.
Okay, well, we have over 150 people watching live, so we have a bunch of questions online, and I haven't been able to follow them while I'm listening to you, but Grant Justice has taken them. So Grant, give us some questions from our audience.
Absolutely. Thank you everyone for tuning in, and I'll start off with some of the easier ones, and also the ones that we get each time. Will Hubble continue its mission after the launch of JWST and now RST, the Roman Space Telescope? And what happens to Hubble when its life is over?
Okay, so I'll take that one because we answer that every now and then at Space Telescope. So Hubble will continue as long as it is producing cutting edge science. Okay, Hubble has been up for 30 years, yes, but it is still producing science that no other telescope can produce. And as long as that is true, that it's really producing quality science, I expect Hubble will probably be funded to continue. The James Webb Space Telescope will be an infrared telescope, and the Rubin Space Telescope is also an infrared survey telescope. So neither one of them will replace Hubble. They will complement Hubble in the science that they do. When Hubble does have, say, battery failures or gyroscope failures or electronic failures and is no longer producing the cutting edge science it needs to produce for it to be continued, the current plan is to let it orbit. It's not doesn't have any problems with orbiting well into the 2030s timeframe. There is a soft capture mechanism on the bottom of Hubble, so if necessary, we can fly a mission up, grab the soft capture mechanism, and deorbit Hubble carefully into the ocean. Okay, Hubble is too heavy to bring down in a controlled, like putting it into a future space shuttle or something like that. And we can't let it just fall willy-nilly. So it would have to be, it would have to have a controlled descent. There are, of course, others who want to just move it up to a higher parking orbit and let it sit there for decades until we can figure out a great way to bring it back down. I mean, everyone would love to put it in the Smithsonian, right? It's just kind of much too dangerous with the current technology. Okay, next.
Gotcha. Okay, so let me take a look here and find our next question. All right, so how many billions of years does it take to build a galaxy that big? Something like the large spiral galaxy that you have in the image behind us.
So you take as long as you can. So I think it's you start right after the Big Bang. That's the thing that I quite love about galaxy evolution. Something like a few million years after the Big Bang happens, you see the first galaxies peak up. Except that these are as big as really some of the clumps of blue that you see in this galaxy, right? They're tiny. They're the little seedlings that you grow a galaxy this big from. I think you need most of the lifetime of the universe to build this. You got all that time, please take it, right? So 13 billion years. It's got a oven time for about 13 billion years. I think it's a slow bake. Since everybody's baking right now, it's a slow bake because I think it has slowly done this star formation about half a solar mass. So it basically produces a sun's worth of new stars every 2 years. That is not the world record in making new stars. That's many times that, but it's been doing it for a very long time, and then you can get there. It probably was a little more active in the early days, but just by having this big disk and just slowly forming stars throughout, you will build a galaxy that big, I think. But yeah, you need I need the whole age of the universe for that.
All right. And the next one, we had a fun time in the comments talking about space dust. So I'll continue that love on here.
Yes.
Could dark matter just be some really, really cold dust and gas that's spread out far away from stars?
Yeah, you'd hope that's the case. At least that certainly was the question that they asked me in 2000 when I started my started grad school. So how much dust is there in these disks, and is it enough to either hide enough stars and then also have enough mass sitting in itself to be the dark matter? There's two things wrong with it. We kind of know how much dust there is now. We've really studied many spiral galaxies, and so we know what the average dust masses are. Simply, we did the accounting. We looked at how much light was missing, and this dust is very much like smog on like a, yeah, if you look at the sunset and it's like, if you're in LA and it's been a smoggy day, you've got a red sunset, right? And so you know how much color change you've got from the stars, you know how much you're missing, but also that dust radiates it back out as infrared light. And so you need to make it very, very cold, and you need to make it a very special kind of dust. I think the technical term is cannonballs. You need to make them very dense, very black, and they're completely away from all the stars, so they don't do much than have gravity and then occasionally block a little bit of starlight. I don't know about you, but that sounds like dark matter to me. And so, but that's the problem for that is that basically you've got this magic stuff that doesn't do anything else, just gravity. And the problem is that we also know where the mass is because we looked at the rotation curve. And you can see where the dust is in this galaxy. It's in the brighter parts of this spiral. And as you go further and further out, I will be the first to tell you that yes, those spiral arms also have a little bit of dust in them, but that's not nearly enough to account for how fast it's rotating. Because,
that kind of leads me into another facet of this.
Right.
Rubin's explanation for how galaxies have flat rotation is that there's missing mass, which is what you were just touching on there,
yep.
Which she called dark matter. But is there another way to account for the observed strength of the gravity other than mass? Is it possible it's energy? Is it possible it's something else?
So,
or we know it's mass?
It has to be, well, it has the characteristics of mass, meaning that it's gravity. It's got a pull. Right? It's got to pull this stuff in and to keep it in its orbit. Energy doesn't have a pull to it, so we need something that exerts a good amount of gravity. So that's one bit. You need stuff to do this.
Yeah, Benne, can I just jump in here a second?
Yeah.
Just to make sure our questioner understands that gravity is a force derived from mass. You're not getting gravity from, I mean, you get the electromagnetic force from charged particles and everything. Gravity is defined as a force. So if you're seeing evidence of gravity, you're seeing evidence of mass. I think they're trying to say, is there something else that could cause these flat rotation curves?
Yes.
But
I do know,
can't formulate it in terms of gravity without being mass, right?
Right. It has to be, if you say it's gravity, there's two things. You either have missing mass or, and that's always a good thing to check, you don't understand gravity as well as you thought you did. And so as soon as those flat rotation curves came out, one of the explanations was that, well, we know how gravity works on the solar system incredibly well. And to the thanks to Newton and later Einstein, we know how it works next to big, heavy, round things. But maybe we don't know how it works on really large scales. So maybe on the galactic scale, we're sort of missing something. And so people have been putting this theory forward as like, well, you should always check whether or not we understand gravity this well on these scales. However, we have some confirmation that galaxies do have a lot of stuff in them from something called gravitational lensing. And this alternative theory called modified Newtonian dynamics, MOND, does have a little bit of trouble making those big structures of galaxies. And so you need a lot of gravity in order to pull everything together. And so MOND hasn't been ruled out, right? So that's something that I want to be very clear about. And I think it's incredibly healthy to just check your work, whether or not you understand the gravity or not. So yeah, curious to see how that plays out.
And Benne, I'd add in that those computer simulations you showed, a lot of those computer simulations are very successful at producing the observed characteristics of gravity, and those simulations have inherent in them the assumption that dark matter is mass and such. So we have a very strong consistency argument for the dark matter there. All right, Grant, got another question?
I do. I just want to take 1 minute to say that that would mean that they are made out of star stuff, wouldn't it, Benne? I couldn't resist. I'm sorry. All right. I have two quick ones, and I think we will call it a stream. Are most galaxies dwarf, and what is the average size of galaxies based on star masses, to your best knowledge?
Off the top of my head, yes. So
yeah, observable galaxies, of course.
Right. So we have I keep telling my students this: if you're an astronomer, you're going to see what you're going to see, and you're going to miss what you're going to miss. And so small galaxies are easy to miss, but there are a lot of them, and so you can only see them in a very small volume. You can only see them very nearby. But they seem to be very, very common. But some big guys like this one, you can see them to much further away. So if you just take you just count whatever you've got on the sky, and you take that at face value, you've overcounted big things like this completely. And so you should go like, oh, monsters are everywhere. But that's not the case. You've just missed all the little things. And so small galaxies of about a billion to about 10 billion solar masses. That's the most common galaxies. Those are the most common galaxies in our universe. They are everywhere, but they are the first things that drop out of your survey. They're the first things, if you start staring, that you pick up. You go like, oh, there's all the little dwarf galaxies. There they are. So they're quite common.
To give people a sense of scale, what would that be in relation to, like, what size would that be? Or a dwarf galaxy, the most common. What would be a benchmark for the audience?
Well, if you look at this picture, I've still got the picture up, you should look at one of these blue clumps on the outskirts. You can see one right, you see that diffraction spike, you see something right underneath there. That's a dwarf galaxy. This thing is like, that would be the size of a dwarf galaxy, but that's not what a dwarf galaxy looks like. That's clearly part of the spiral structure of this whole thing. But yeah, the dwarf galaxies,
it gives an idea of the sense of scale.
They are much smaller. They're dwarfs.
Yeah, and using the numbers that you provided, if this is 1 trillion solar masses and a typical galaxy is 1 billion solar masses, that's 1/1000th the size of this galaxy. So and that's just in the stellar mass. That doesn't include the dark matter in it there. So that gives you some numbers. Also, in the local group of galaxies, we have about 36 galaxies. Only 3 of those are big galaxies: the Andromeda, the Milky Way, and M33. The rest are these small galaxies. So even locally, the dwarfs have inherited the universe
by a landslide. All right, and the last question. One of the things that you noted was that globular clusters have a tendency to stay together in this almost spherical pattern. Do they break apart when they are devoured by another body, or when they interact with other galaxies, or do they tend to keep their cohesion?
They tend to stick around, and the reason for that is not because of dark matter. They are just a really dense grouping of stars, so they kind of stick together based on that. So while the more extended galaxy is tidally stripped and into these streams, the globular clusters themselves stick around. They start orbiting the bigger galaxy. So you tend to find the globular clusters long after the parent galaxy has been shredded by the encounter. And not only that, we've actually seen some strings of globular clusters that clearly have a different color than the rest of them, and so they must have come from another galaxy, and so they're still following the old galaxy's orbit. But they definitely seem to survive pretty well. They survived our own Milky Way for a few billion years. So yeah.
All right. Well, thank you, Benny. Thank you, Grant, for providing the questions. And thank you to our audience for showing up. This was our very first online only public lecture series. We will be doing them again every month. We're going to try and keep to the first Tuesday of the month date. But we'll have to figure out whether or not it works doing that like this in the afternoon, or if it might work better if we do it back at the 8 p.m. in the evening. We'll probably survey the folks on our email list to find out about that. Next month, again, Interstellar Comets by Amaya Morrow Martin. Going to be a cool talk. Let us give one more virtual round of applause for Benne, and thank you all and have a great day.